Today we're going to talk about compositions of functions. And before we can get started on that compositions of functions, I want to make sure you understand function notation well. So we'll start with that. You've seen that in the past. If we had something like y equals 2x plus 5, y is a function dependent on x. So we can write that as f of x equals 2x plus 5. Because this is the same thing, a function dependent on x. That's what that stands for there. Now, in this case here, we would have to say x is equal to 2, and then you would take that 2 and you would plug it in for the x in this equation. With function notation, we write that as f of 2. That means my x is 2. So I would substitute this x with a 2, only the x. So I replace this x with a 2, and then I can simplify that. So I can say f of 2 is equal to 4 plus 5, which is 9. Function notation is important, especially with really long problems, because at the end it shows you what you were looking for in the first place. It allows you to use multiple functions because sometimes you'll see an f of x is equal to 2x plus 5, and g of x is equal to 3x minus 1. And then they can give you an h of x or a j of x. So it can use a number of different functions, and you can know which one you're talking about by f of x or g of x or so on. With y, you would have to label them all the same, so it doesn't make it as easy. But this is just a function dependent on x. That's what that means. And so the x is inside my equation. It's my independent variable. And when we do something like this, you are just telling it the x is being replaced by 2. So you replace the x with 2 in the equation. When we do compositions today, you're going to use that same concept. So I wanted to make sure that we went over it before we started on our compositions. All right, here is the main notation you're going to have to know. So we want to go over that part. Here's our function properties. If we're given two equations, f of x and g of x, to say add or subtract those, we would say f plus g of x or f of x plus g of x. Both of these mean exactly the same thing. They mean to add the two functions together. If there's a minus between them, then that would mean to subtract the two functions. If there's a dot, that means multiplication, or if they're side by side, that means multiplication. And then in our last case here, if there's the division, that means divide. And again, both of them mean the same thing. The notation is just written a little differently. This last one here with this open circle in the middle means composition. That's the same thing as this one right here. This also means composition. With composition, we are putting one function into the other. So it's not operations like these right here where we were adding, subtracting, multiplying, dividing, which is something you've done all the time. But this open circle is when you are composing one function from another. So you're putting one inside of the other. That's the one that we are going to focus on, is the compositions. A lot of times you'll see this on SATs. That's what that means, is that composition. All right, we're going to start graphically because students seem to find that a little bit easier. So looking at these right here, this says f plus g of 3. I'm going to go ahead and write it the other way because I actually prefer the other way as well. So this is the same thing as f of 3 plus g of 3. So our x value is 3, and we're looking for what the y value is in the f function. In this case, the x value is 3. We're looking for what is the g function. So when we look at a graph like this, it tells us that f of x is the parabola. So this is our f of x function right here. And this is our g of x function. So that's important. See, this is that labeling where if we just did y equals, this would be harder. But because it's the f and the g, then we know which function it's talking about. They're labeled differently. So for f of 3, I would go to 3 on my x here, and I would go to the f function, which is the parabola. So right here, it is at 5. So this would be 5. I go to 3, and then I go to my g function. That one is at 4. So 5 plus 4 is 9. For subtraction, we're doing the same thing. And again, that could be rewritten as f of -2 minus g of -2. I prefer it this way. I feel like it makes more sense, but some people like it better this way. It's up to you on preference on which way you like it. So here we go to -2, and my f function is right there at 0. It hasn't gone anywhere. My y value is 0 right there. And then I go to -2, and my g value is right here at 2. So that would be 0 minus 2, which is -2. All right, we'll do a multiplication and division as well. So this is f of 0 times g of 0. That means the x value is 0. So I go where my x is 0. My f function is right here at -4. My g function is right here at +4. I multiply those two together and we get -16. All right, we're going to try our D1 here, which division. And so that is f of 1 divided by g of 1. So I go to 1. My f function is at -3. I go to 1, and my g function is at 4. So that is -3/4. I'm going to do one more here because order matters, especially with the division one here. My f is first, so that's my numerator. In this case, my g is first. So that's going to be my numerator. So that would be g of 2 divided by f of 2. I go to 2. My g is right up here at 4. I go to 2, and my f function is right here at 0. Now we know we cannot divide by 0, so this is undefined. All right, now we're going to talk about these compositions. We said that is putting one function inside of the other. And again, I prefer the other notation, so I'm going to rewrite this as f of g of -3. With compositions, you want to work from the inside out, so it's telling you -3 is the x value in the g function, and all of that is going to be the value of x in the f function. So I'm going to go to -3, and then I go to my g, and it is at 1. So this entire part right here has a value of 1. So we get this right here, f of 1. So now what we're saying is the x is 1. What is the f? So I would go to where x is 1, and my f function is at -3. So unlike the other ones, we're not finding that same x value. We are replacing, our input becomes different than the other ones. All right, let's try that again right here with f of g of -1. I start from the inside, so I go to -1. My g function is at 3 right there. So I'm going to replace this entire inside part here with 3. So I get f of 3 is equal to, I go to my 3 on the x here, and my f function is right here at 5. So this has a value of 5. And again, order matters. So in this case here, we're placing the f inside of the g. I can rewrite that as g of f of -3. I start from this inside, so I'm going from -3 in the f function. So I go to -3. My f function is at 5. So I get g of 5. I'm going to go to 5. It's all the way at the end here. And my g function is at 3. And so there is my g of 5. All right, now we're going to talk about these algebraically. What's happening when we do this algebraically? Again, we get to have more than one function if we don't put that y equals. And so here we're saying f of x is x squared plus 1. G of x is 3x minus 5. So if we've got f plus g of x, we're saying we're going to add this entire function to this one. So we get x squared plus 1 plus 3x minus 5. We took all of f of x and added it to all of g of x. In this case, we would combine our like terms, and so we get x squared plus 3x minus 4. So that is f of x plus g of x. All right. For minus, same thing. It is f of x minus g of x. Now this one you want to be very careful because of this minus sign here. You are subtracting the entire function. So this would be x squared plus 1 minus that entire function of 3x minus 5. A lot of people remember to subtract the 3x part, but they forget that they are subtracting this last value as well. So putting parentheses there keeps that organized and helps you remember to do the entire thing. So I would distribute my sign, and then we would combine our like terms, and we get x squared minus 3x plus 6. Oh, you can't see that. Sorry about that. So we went ahead and distributed that negative sign, and then we combined our like terms. So these you've done already. You've done these operations. It's just the notation here that's different for you. The compositions will be completely different, but the adding, subtracting, multiplying, and dividing you have done already. All right, so we'll look at C there. It says f times g of x. Sorry, you can't see those equations anymore. There we go. So we've got f of x times g of x. So we would take our entire f of x, which is x squared plus 1, and we would multiply it times our g of x, which is 3x minus 5. You've done this before. This is FOIL or the box, whichever method you use to multiply two binomials there. So we would FOIL here, x squared times 3x gives us 3x cubed. X squared times negative 5 gives us a negative 5x squared. 1 times 3x gives us a 3x, and 1 times negative 5 gives us a negative 5. Again, you could have used the box with that or whatever method it is that you use to distribute those, but it's multiplication. All right, for this one, we've got f of x divided by g of x. And so I get x squared plus 1 over 3x minus 5. Although this one looks harder, we just got out of our rational unit, and we know that if these are not exactly the same factors, they cannot reduce. So that is my answer right there. Of course, you would restrict it. X cannot be 5/3, since that's what makes that denominator 0. All right, on to the composition part, which is the new part. We've got f composed of g of x. Again, I like to write it this way better, but it's whatever you prefer on that notation. So this is f of g of x. This is saying we are going to take the g of x function and we are going to plug it into the f function. So I'm going to take this entire thing, 3x minus 5, and I'm going to plug it in for the x in this function. Some people will write it out in steps, so I'll show you that part first. I'll do the 3x minus 5 inside here. So I replaced this g of x right here with that 3x minus 5, because that's what g of x is. G of x is 3x minus 5. So I substituted that there. Now I'm going to substitute 3x minus 5 for the x here, just like we did when there was a number there. And so we get 3x minus 5 squared plus 1. This was x squared plus 1. All I did was take the x and replace it with 3x minus 5. The squared plus 1 stayed exactly the same. So the only thing you're substituting is that input value. And then to simplify, just like we did here where we multiplied, you would FOIL or distribute or use the box, whatever you use, for 3x minus 5 squared. That is 9x squared minus 30x plus 25 plus 1. I combine my like terms. And there is f of g of x. We're going to try that again. And the order does matter. This one here has the f of x inside of the g of x. So we would want to do the same thing. Again, you could go piece by piece. And so we can get g of f of x is x squared plus 1. So that's what I would replace there. So f of x is x squared plus 1. So all I did was replace that in there, substitute it in. And now this is saying g of x squared plus 1. So we would take all of this and plug it in for the x in the g function. And so we get 3 times x, which is x squared plus 1 minus 5. So I have not changed the equation. It is 3. This is my new x minus 5. So it's exactly what it said here, 3x minus 5. The x is now x squared plus 1 because we replaced it with that. And we distribute and combine our like terms. So that is compositions. We're going to look at a couple more of those compositions just to make sure that you understand them. So here is some more practice ones. We're going to do f here, f of g of x. Here there are 4 functions. That's why I told you that function notation is actually useful because you get to use, you can label them as many functions as you want and still be able to know which one we're talking about. So here we're saying f of g of x. So we're going to take this g of x, x squared, and we're going to plug that in the middle. So I'm going to get f of x squared. And then this is my f function. So I'm going to replace the x with x squared. That's what this means here. And so we get f of g of x is equal to 4 times x, which is now x squared plus 2. Not much to this one. I just distribute that, and there's no like terms. So there we go. Here is another example, g of h of x. So in this case, I'm going to go ahead and replace this h of x with 2x minus 3, because that's my h of x function. Now we're going to go ahead and go to the g function. That's this one, x squared. And I'm going to replace that x with the 2x minus 3. That's what this means here. And so we get 2x minus 3 squared. And then we would use FOIL or box to simplify this out. And we get 4x squared minus 12x plus 9. There's another one here, h of f of x. All right, so first thing I would want to do is figure out what is f of x, because that's going to go inside my h function. And f of x is 4x plus 2. So we're going to plug that in there. Now to find the h of f of x, we take this 4x plus 2, and we're going to plug it into the h function for the x. And so there's the h function, 2x minus 3. So I'm going to replace that x with the 4x plus 2. So we get 2 times 4x plus 2 minus 3. I've replaced the x in that equation right there. We distribute and combine our like terms. So those are compositions. You can have more, just like we have down here, j of f of x. Again, you would work from the inside, so we'll do this one here. I get j of f, and g of x was x squared, so that's going to be my inside term there. Now I'm going to take that x squared and I'm going to plug it into the f function. So this is my f function right here. So I'm going to replace that x with the x squared. And so I get 4x squared plus 2. So all of this right here became this part right here. And then we do the substitution one last time, and this becomes the x in the j function. And so our j function is this square root of x plus 3. So I get the square root of 4x squared plus 2 plus 3. This was the new x. The plus 3 still came from the equation, so we did not change that part. To combine our like terms there, we add the 2 and 3. And so that is our final equation.